like carefully quantify amounts in chemical reactions, Avogadro developed um, a lot of these important ideas about ratios. So you can read about Amadeo Avogadro. And anyway, Amadeo Avogadro developed this concept of the mole. Okay, so now say a thing about mole. You know, we had Mole Day back in October, and Mole Day is like the annual celebration for chemists. And the quantity, the mole, is not actually related to like the animal, the mole, but you know, like we have a word in chemistry, molecule, and mole refers to like a chunk or quantity of. So when we say a mole of something, we're talking about like a quantity of it. The same as like water molecules. Each water molecule is two hydrogens and oxygen. That's one chunk unit. That's one thing. So it's not the animal, but we also use this, you know, little like caricature of a mole, like, you know, a small rodent, to be our like kind of mascot for the concept of the mole. So the guy is Amadeo Avogadro. All right, the name Amadeo Avogadro. And there's a number that we use in modern times to describe quantities of matter, and that's called Avogadro's number. People also call it the mole. So Avogadro's number is this quantity here, 6.02 times 10 to the 23rd. We abbreviate it as n sub a. So anytime you see like n sub a, n is always like an abbreviation for like a number, and then the sub a is for Avogadro. So n sub a literally means like Avogadro's number, and Avogadro's number 6.02. A lot of times people write it's actually 6.022, but for this course it's good. 6.02 times 10 to the 23rd. That's Avogadro's number. Okay, so what does Avogadro's number mean? We count things in different quantities. Like 12, you call that a dozen. So anytime sometimes you got a dozen of something, you got 12 of it. Well, if you have a mole of something, you have this many, 6.02 times 10 to the 23rd. It's a much larger quantity. See, like atoms are very, very tiny. So the fact is, if you're going to count up atoms in a quantity that's useful to talk about, have in the laboratory, you've got to count them in huge numbers to be able to make it like a reasonable value. So if you write out Avogadro's number, like instead of 6.02 times 10 to the 23rd, I mean, this means 6.02 times the quantity, 10 to the 23rd, it's writing this out, 602, and then you write 602 and put 21 zeros after it. That's the amount in chunks that we count atoms out by. Now, it seems like a random number. It's like a large value, and it seems like a random value. Like, why not make it like 1 times 10 to the 23rd, or make it like, you know, 1 times 10 to the 24th or something? Why is it this particular number? And it's related to a thing on the periodic table. So Avogadro's number is actually rigged so that the masses that are on the periodic table have a special meaning. And here's how that goes. Like for hydrogen on the periodic table, in the upper right-hand corner, there's a 1, that's its atomic number. But you know this 1.01 that we've been using? That 1.01 has like has 2 different meanings. Its first meaning is that it's the mass of one atom is 1.01 AMU, but we also write 1.01 U. But the other use for that number, and it's why Avogadro's number comes out to be this value, is that based on the metric system, we have rigged it so that's also the mass of one mole in grams, meaning it's 1.01 grams per mole. So one individual atom has a mass of 1.01 AMU, but if you have this many, like this 6.02 times 10 to the 23rd, this quantity of hydrogen atoms, they have a mass of 1.01 grams, which is about the mass of a paperclip. And that's a useful small quantity that you could weigh out in the laboratory. So different atoms have different masses based upon those quantities. It's like you know, you could count out eggs. Let's say you've got a whole lot of eggs. Say you have got thousands of eggs, and your job is to count them out. You could count them out, or you could figure out like how much one weighs, and then weigh the whole lot of them, and divide the total weight by how much one weighs. But there's a problem with dividing by how much one weighs, and that's that you end up with issues with precision and accuracy. So a smarter thing to do is to weigh out like a dozen of them. It's quick and easy to count 12. You can weigh 12 of them, which is going to weigh, more than one. And then if you divide the total mass of this huge quantity of eggs by the mass of a dozen eggs, it tells you how many dozen eggs you got, give or take a little bit. And it's actually more precise to do that. So it's simply impossible in our lab to count individual atoms. You just can't do it. You also can't weigh individual atoms because they just don't weigh much. But what you can do is get big chunks of them, this molar quantity, and weigh them out in those large quantities. Okay, so here's another concept. You got cookies, we got cars, we got aluminum atoms. And it doesn't matter if you got a dozen cars or a dozen cookies or a dozen aluminum atoms, you still got 12 of each. Like 12 cookies is, you count to 12, that's how many cookies you got. You can count to 12 cars, now you got, 12 individual cars, or you can have 12 atoms of aluminum. You can also have a mole of cookies or a mole of cars. That's more cars than have ever been manufactured. And a mole of atoms, mole of aluminum atoms. What's the same about all those things, cookies, cars, or aluminum atoms, is when you talk about the quantities, they're all identical. But the mass of a dozen cookies and a mass of a dozen cars is going to be wildly different. Similarly, the mass of a dozen aluminum atoms is going to be totally different. So as a measurement of quantity, they're always the same. But measures of mass, it's going to be different. So like a dozen cars is going to be really heavy. A dozen cookies is going to be some kind of medium weight. And a dozen aluminum atoms is going to be very light. But no matter what, if you have a dozen of any of those, you still have the same relative quantity. So you can have this ratio, like a ratio of mass to numbers. Here's some, I guess, fun facts or whatever. To give you a sense as to the scale, one scale you can use is if you had a mole of softballs, that's 6.02 times 10 to the 23rd softballs, they would just about fill the Earth. So if the Earth itself was like a hollow sphere, you started sticking softballs in, you need a lot of softballs because the Earth's pretty big. It takes about a mole of softballs to fill the Earth. So, the Earth itself is pretty huge, and a softball is, ridiculously tiny. So it helps to illustrate the relative quantity of them. On the periodic table, the concept is that when you see like carbon and it has 12.01, that 12.01 now not only is an atomic mass in U, this can be written as a conversion factor. It's 12.01 grams per mole. So you can also write that as 12.01 grams divided by mole. So just the same as we use other conversion factors to convert between length units or mass units, you can use the formula mass or the molar mass on the periodic table to convert between masses and quantities in this quantity to mole. All right, so here's a, let me see if I got one. Yeah, we'll get to it. All right, so here's another thing like in the laboratory, just to give you a sense. Those are on watch glasses and beakers. Because different elements have different masses, they're going to take up different amounts of space and they're going to weigh a little bit different. And the materials have different density as well. A mole of water is about 18 milliliters or about 18 grams. Uh, Sugar, like sucrose, C6 or um, well, it depends. I guess if it's sucrose, um, like C12H22O11, because its mass is very big as an individual compound, it's a pretty big pile of sugar to have 1 mole of sugar. But then water, H2O, its mass is only like 18 grams per mole. So it's a little bit of water in a beaker or a pretty big pile of sugar. So when they're equal quantities, they're not always equal masses. That's the other challenge in the laboratory. So when we balance chemical equations, we say, oh, we need 2 of these for 1 of these. It doesn't mean that it's twice as much weight of this for 1 of this. It means that twice as much quantity of one as the other. But the quantity is the number of them. Then you've got to convert from numbers of them into relative masses. So here's a way that you can use it as a conversion factor. And we'll use water as an example. So on the thing here about conversions, where it says like mole map part 1, let me give you an example. Let's say we've got some water. And whenever you want to find the formula mass for water, you've got 2 hydrogens and 1 oxygen. Hydrogen has a mass of 1.01 and oxygen has a mass of 16. So 2 hydrogens have a mass of 2.02 and oxygen has a mass of 16.00. So just the same as when you calculate formula mass in U, maybe use that to find a percent composition, this is also 18.02 grams per mole. So here's what that means as a conversion factor. You can write 18.02 grams per mole in one of 2 ways. You can write 18.02 grams divided by 1 mole, or you could write it as 1 mole divided by 18.02 grams. Because the conversion factors can be switched upside down. It's exactly the same as using a conversion factor like, there are 3 feet in 1 yard, or you could write that conversion factor as 1 yard over 3 feet. And if you remember, we did some stuff with conversion factors like earlier in the course. The concept with a conversion factor is that the value in the numerator and the value in the denominator, they're equal to each other or they're equivalent to each other. So here's the concept, like the mole map or the concept map. If you have a mass in grams and you want to convert it into a number of moles, you can multiply by a conversion factor where the unit grams is in the denominator and moles is in the numerator. And then that'll give you some quantity in the unit the mole. Or maybe you have a quantity in moles and you want to figure out the mass because you want to like weigh something out in the lab. Then the conversion factor has moles in the denominator and whatever the mass in grams is in the numerator. And that'll get you like a mass in grams. So the 2 conversion factors are either the mass in grams over 1 mole, or moles over whatever the mass is in grams. And you just add up the masses for the compound just as it appears. If it's a single element, all you gotta do is look up the number on the periodic table. That's all you gotta do. So we'll do some examples because that'll give you like a practical sense of like what the meaning is here, why we do it the way we got to do it. But those are the two different conversion factors, either moles over grams or grams over moles. And the thing about conversion factors is the plan is that whatever unit you start with, grams, that's the unit that goes in the denominator of the conversion factor. But if you start with a quantity in moles, then moles goes in the denominator of the conversion factor. Okay, so the first example, this is like on the bottom of the guided notes. Example number 1. Aluminum is a lightweight, very strong metal. It's used in tennis rackets, used in ski poles, tent poles, bike frames, baseball bats, softball bats, coat hangers sometimes. It's used a lot for building aircraft because it's a fairly lightweight, strong material. So you have 3 moles of aluminum. So there's two different ways to see that idea conceptually. 3 moles means that you have 3 of those units, 3 of those quantities of aluminum as like chunks. So this 3 moles is the same as 3 like times the quantity for a mole. So it turns out that 3 moles happens to be about, whatever 3 times 6.02 times 10 to the 23rd, which is 1.806 times 10 to the 24th atoms. But we want to convert from mass or from moles into mass. So what you always do is start with the quantity in moles, 3.00 mole, and then we want to convert that into grams. So the conversion factor has to have the unit mole in the bottom. 1 mole has a mass in grams. And what that mass is just whatever is on the periodic table. On the periodic table over there, or the one you have on paper, you'll find that for aluminum, Al, it's around 26.98 is the mass on the periodic table. So that means that 1 mole of aluminum has a mass of 26.98 grams. So this molar quantity, and the abbreviate, this is, it's kind of weird and sort of annoying. The word mole is MOLE, but the abbreviation is just MOL, which isn't much of an abbreviation. You know what I mean? You just take the letter E off it. So I'm not misspelling it. In prose, mole is always MOLE, but as a unit, it's always MOL. So I don't know. There's a whole lot better abbreviations we use in science, but MOL is what we use for mole. So now the math goes, you got 3 moles times this factor, 26.98 over 1. The math is just, you take 3 times 26.98. And it's important to follow significant figure rules. This comes out to be, on my calculator, it says 80.94. But the 3.00 only had 3 significant figures. So although the 26.98 has 4 significant figures, it's appropriate to express this answer with only 3 significant figures. 80.9 grams. So here's what that means. If you have a chemical reaction that you're trying to make happen, maybe it's a reaction where you've got aluminum and oxygen. So this is actually a good example because I can make up this reaction. If you take aluminum and react it with oxygen, that makes this compound like Al2O3, which is aluminum oxide. And if you want to balance this equation, I got to put a 3 here and a 2 there. Oh, it comes out to be 4. Anyway, if you wanted 4 moles of aluminum, it would be, bigger than 80.94. I'll just show you that real quick. If it was 4 moles of aluminum, 4 times 26.98, 107. So if you wanted to make this one reaction take place with 4 aluminums and 3 oxygens, the mass of aluminum you weigh out is whatever 4 times 26.98, 107.92. And then if you wanted to have the right amount of oxygen, you have 3 oxygen molecules with their appropriate mass, and that gives you the appropriate mass of oxygen. So this one is converting from mass, or from moles to mass. To go from moles to mass, you just take the number of moles first, you put 1 mole in the denominator of the conversion factor, and the numerator is the mass from the periodic table. If you want to go the, let's see, I guess the next one is, yeah, you got 0.0342 mole of silver. And you're trying to convert that into a mass. So how many grams? Well, 1 mole is in the denominator, and then you look on the periodic table, and it's 107.87. There's no math to do because it's just a single element. But this 0.0342, that has 3 significant figures. And the 107.87, that has 5 significant figures. So the answer should only have 3. 0.0342 times 107.87. Well, so my calculator says 3.689154. That's way too many digits. We want to round this up to only 3 digits. 3.69 grams. So if you needed this quantity, 0.0342 moles, you'd actually weigh out 3.69 grams. So that's one more example of going from moles to grams. So then like number 3 is going from grams to moles. How many moles are there in 45.05 grams of water? So you can start with the 45.05 grams. And now water, well, I figured this out before, but I'll just write it again. You got hydrogens, you got oxygens. There's 2 hydrogens, 1 oxygen. Hydrogen has a mass of 1.01. Oxygen has a mass of 16.00. So it's 18.02. That's the mass of water. This is in grams per mole. So if you want to convert from a mass in grams into a quantity in moles, because the mass is the unit you start with, you're going to put the 18.02 grams in the denominator and 1 mole in the numerator. The unit grams cancels out and leaves you with the unit, the mole. So 45.05. Yeah, so that's exactly, let's see, 45.05, 18.02. Yeah, it comes out to be exactly 2.5, but because each of those values has 4 significant figures, this should be expressed with 4 significant figures. So 2.500 is the correct quantity in mole. And, you know, this whole idea about having 2.5 moles is that because Avogadro's number is that a mole is equal to 6.02 times 10 to the 23rd of anything. They could be atoms, they could be molecules. You can then convert this quantity in moles into numbers of molecules. So how many water molecules are actually present in 2.5 moles is the same as going 2.500 moles. And then Avogadro's number can be used as a conversion factor, where every mole is 6.02 times 10 to the 23rd. And that gets you the number of molecules, 2.5, 6.02, 1.505 times 10 to the 24th individual molecules. So this is how many individual molecules are present. If you have 45 grams of water, which is like, that's pretty close to 45 milliliters of water, that'd be like like a water bottle about 1/20th full has a mass of about 45 grams of water in it. That's 2.5 moles of water. And in number of molecules, it's that many molecules. And then it turns out that because every molecule has 2 hydrogen atoms and 1 oxygen atom, this number of molecules then tells you that it's 3.01 times 10 to the 24th atoms of hydrogen and 1.505 times 10 to the 24th atoms of oxygen. So if you happen to have like 45.05 grams of water, kind of like about that high in the bottom of a water bottle, you can then count up or approximate the number of atoms that are actually present. So we we could count up atoms in different quantities. We could always do all the math in terms of numbers of individual atoms, but because the atoms are so tiny, we'd be writing these enormous numbers to represent total quantities of atoms. It's just much smarter to weigh stuff up and count stuff up because they're so tiny in these bigger quantities. And then we rigged the value for Avogadro's number so that it is a value that makes it for the metric system to have the formula mass on the periodic table for any element, like oxygen 16.00, to have 2 meanings, both the mass of an individual atom in atomic mass unit and the mass of a mole of those atoms in the unit the gram, which is what our balances measure out. If you were to do chemistry not using the metric system, like using pounds or ounces, then you'd use a different conversion factor and different masses. But the whole world uses the metric system, the masses in grams. We always let's see. All right, so you have that. There's a second paper, right? One says moles to grams, grams to moles. So at the top, there's just a little bit of practice finding masses of compounds like sodium fluoride, ammonia, phosphoric acid. And then the 2 conversion factors are written in there too, how to get from the molar mass to number of moles. So that molar mass, we actually call it a bunch of different things. I'll tell you all the things that you'll see. This 16.00, I guess, well, it depends upon the compound. So for instance, for water, that 18.02, it's called a bunch of things. You'll see it called the formula mass. It's also called, like, people call it the molecular weight. People call it the molar mass. It's kind of improper to use the word weight because weight is actually in a different unit, not the gram. If it's an individual atom, it's called the atomic mass. They're sort of interchangeable. We use them in different ways. Like it's sort of improper to say molecular weight. Formula mass is kind of most preferred. But if you're talking about doing a conversion factor between moles and grams, then it's appropriate to say molar mass. But it's inappropriate to say that this is an atomic weight because it's not just the mass of an individual atom. If it's oxygen, that's appropriate to call it the atomic weight. So here it's appropriate to call it like the molecular mass or the molecular weight. And then there are 2 examples on there, getting from like mass in grams of lithium into number of moles, and from moles of sulfur into a mass of sulfur. So there's 8 of them on here for you to practice. Converting from grams of argon into moles, converting from moles of magnesium into grams, converting from moles of sodium fluoride into grams, a couple more on the back. So you got to always have a periodic table handy. And then I'll tell you a thing about the calculator. you have like the TI calculator emulator app on your Chromebook. There's a couple different ways to enter values in scientific notation, and I actually don't have that app, but your screen is like this. And then the number keys like 1, 2, 3. Above the 7 key, there's a key that has a comma in it. And above the comma, it has a little EE. And that EE that's in yellow is in reference to another key that's in the upper right-hand corner that says second. And it's possible, depending upon the emulator, it might be a different color. Some of them it's blue, but it really doesn't make a difference. The best way to like enter a value that's related to Avogadro's number, like 6.02 times 10 to the 23rd, you can enter a couple different things on the calculator. You can type 6.02 and then actually hit times and then hit 10 and hit like caret 23. And that's okay. But above the 7, that comma has that EE. And that EE is specifically used for scientific notation. And how you use that helps in a couple different ways. How you would enter the value 6.02 times 10 to the 23rd is by typing 6.02, and then you actually hit the second button because that then accesses the EE for the comma. This really has the meaning EE. And then you type 23. So when you hit 6.02 and then hit second EE 23, it's actually fewer keystrokes than hitting 6.02 times 10 to the 23rd. But there's another reason why it's good to use the second comma to do 10 to the 23rd. And that's because if you enter a value like 6.02 times 10 to the 23rd, your calculator doesn't distinguish between the 6.02 and the 10 to the 23rd being all together in one operation. So here's what I mean by that. If you were to take like, let's say you take 3 divided by 6.02 times 10 to the 23rd. If on your calculator you type 3 and then divide by 6.02, that one went away, that's weird, times 10 caret 23, this is not what your calculator will do. What your calculator is actually then doing is this, 3 divided by 6.02 times 10 to the 23rd. Puts the 10 to the 23rd in a totally different place. So this is the incorrect way to do it. So in order to do that correctly with the 10 to the 23rd, you have to type like 3 divided by, open a parenthesis, 6.02 times 10 caret 23. So you not only have to type times 10 and caret, but you also got to have a parenthesis there, which is a pain. So instead, the quick way to do this is just to take 3 divided by 6.02. Your calculator will actually show you an E on the screen, E23, because when you type 6.02 and then the second comma 23, 6.2 times 10 to the 23, it'll always group that together. It won't think the 10 to the 23rd is like possibly up in a numerator instead. So I don't know. I know that like it depends on who you have for a math class and when you first use the TI calculators, whether or not they show you about the EE function. And so another thing that's true is when you type 6.02 and then you hit second comma 23, the calculator screen will actually only display this 6.02 E23. It won't have 2 E's. It'll only have a single E. There it goes. And that Zoom like quit. I don't know. Zoom's been bad this morning. First period, I got like kicked out of it twice. like Zoom just shut down and I had remote students and they were like, "What's up?" And then I had to get back on the Zoom